Assalamu alaikum. Our paper title is Texture Enhanced 3D Unit with Deep Shortcut for Brain Tumor Segmentation. So here are the authors. I am Mahir Abrar Khan, will be presenting this paper. So this is my contents of presentations. So to begin with introduction, our work is about image segmentation, which is a computer vision technique that partitions a digital image into discrete groups of pixels, image segments, to inform object detections and related tasks. So common applications are given, such as medical imaging, as you can see in figure 1. So also there are various other use of the segmentation, like autonomous vehicles, robotics, agriculture, and gaming. So we'll be dealing with brain tumor segmentation. So the background is given here. Actually, brain tumor segmentation from multimodal 3D MRI is essential for clinical diagnosis, treatment, planning, disease monitoring, and another one is tumor heterogeneity, low contrast boundaries, and class images make automated segmentation challenging. So this is the one of the challenge, and in some cases, deep 3D CNN-based methods achieve high accuracy, but it requires heavy computation and large memory resources. So in the given background, our motivation is to develop a model keeping in mind that existing deep architectures are inefficient and difficult to deploy in resource-constrained clinical environments. So we will be working on a base architecture and try to improve the uh, performance measure and efficiency measures of the base models. So lightweight models reduce complexity but often overfit and lose performance on unseen data. So there is a need for an efficiency-aware segmentation model that preserves accuracy while significantly reducing parameter and floating point operations. So here are the related works that we have used as a baseline. So as we can see in the first one, it's a encoder decoder based architecture, and deep attention mechanism are used here. So the dice scores are given, and in the second paper, deep supervision is used, and auxiliary losses at intermediary layers are used in this model to stabilize the training, and particularly effective for delineating the small and ambiguous tumor structures. And in third paper, it's the SWAN UNet architecture, which used SWAN transformer model as a windowed self-attention as the SWAN transformer model. As we know, in the SWAN transformer model, as we know, windowed self-attention captures multi-scale context with controlled complexity, and also 3D unit and encoder-decoder architecture is used with transformer encoders, which improves global and local modeling of the image. So the dice score also given here. So as a problem statement, we have stated 4 points. That is, segmenting brain tumor subregions is a challenging task, and computational heavy volume data remains challenging. Uneven tumor regions degrades the segmentation quality, overall segmentation quality in average. So brain tumor segmentation is highly also impactful in tumor diagnosis. So our target is to develop such a model that will segment brain tumor efficiently. So here are the objective. The first objective is to use the full volumetric inputs of 3D MRI images, which we can find from Brett's dataset. So the dimension is 155 into 2 times 240 times 240. So then our another objective is to improve the detection robustness, particularly for minority tumor subregions. So our third objective is designing a lightweight solution which substantially reduce parameter count and floating point operation to support practical and resource efficient deployment. So this is the whole methodology, as you can see. So in this methodology, if we go, here is a deep shortcut, and we can say fusion. From the input is fed into the encoder decoder architecture with fusion from the input image. Also used a deep shortcut at the output layer, before the output layer. So this is the overall architecture of the whole solution. So here is the basics that I have just said. Built on 3D encoder decoder unit backbone, uses skip function to preserve spatial detail, enhanced with learnable texture features, which is called LTS in short. LTS is injected using channel recalibration and deep shortcut. So LTS is the as we can see this const 3D. The input is fed into this const 3D, and the output is fused with input again. So this is what we are calling the LTS model, which afterwards goes to squeeze and excitation block for channel recalibration purpose. So, so just as I have said, so this is the LTS model, LTS block. The learnable texture extractor uses 3D convolution layers to generate texture feature maps. Texture features are learned end-to-end, lightweight, and fully differentiable. These features are fused with multimodal MRI inputs via channel concatenation. So this is the fusion strategy. So texture maps are fused early in the encoder. Fusion preserves the fine-grained local patterns important for tumor boundaries and heterogeneous regions. Unlike handcrafted texture methods, this approach requires no heavy pre-processing as this is a learnable texture feature, and this block adapts automatically to data characteristics, and description excitation is applied after texture fusion, while global average pooling captures channel-wise importance. A lightweight gating mechanism suppresses the redundant channels and emphasizes the informative texture and modality features. This shortcut is introduced to prevent texture feature degradation in deep layers. So in summary, this is the overall methodology. So we can see the base 3D encoder decoder architecture, which is optimized in depth. Uh, so this is an inspired one. The reference is given in this slide at the last. So now comes the implementation part. So here we have talked about the dataset, which is the Brad's dataset. So there are actually 369 training, 125 validation, and 166 test multimodal brain MRI studies. Each study has 4 MRI images, including T1 weighted, post-contrast T1 weighted, and T2 weighted, and fluid attenuated inversion recovery sequences. Here are the enhancing tumor, peritumoral edema, and necrotic, and non-enhancing tumor core were annotated. As you can see, T1, T1C, T2 there. So we can see 3 different colors: green, blue, and red. So these three different color indicates 3 different tumor region. So for implementation, our training strategy for the hyperparameter is given here. As you can see, learning rate of 0.0001 and 20 epochs with batch size 1 was used, and cross entry loss was used. So this is the implementation part where we are showing the uh, input and output dimension and the number of channels for each encoder block. So these are the some of the feature map for at each layer that you can see. We can see some shapes are taking place. So this is the decoder block, input and output dimension calculation and channel number of channel calculations. These are the some output some of the feature maps at each layer of the 4 decoder blocks. So in this table we have showed parameter and flops count for each of the block from encoder 0 to 4, encoder 0 to 5, and decoder blocks and final conclusion there. So on the left side we have given the base model for the base model, and the right side we have the proposed model. So we can see in encoder 4 block there is no parameter number is 0, which means we have eliminated the encoder 4 and 5 block. And we can see in the proposed architecture that we have eliminated the decoder 3 block and decoder 4 block. Instead of that, we have introduced LTS block that we have showed earlier and the deep shortcut strategy. So these are the parameter count and the floating point operation count. So these are the ablation details for depth optimization. We can see the depth for depth 6 and 4, and also we have done our ablation study with the texture and without the texture. So we can see that when we were not applying texture block, LTS block with the channel recalibration and deep shortcut, when the depth is reduced, we can see a slight degrade in performance, but the parameter count and flops and latency is optimized. But then again, when we applied the texture block with the reduced depth, the result is up to the mark again, and also the parameter count and flop for floating point operation are much less than the base architecture. So these are the now comes the result part, where we have showed the dice, weighted average dice, and imbalance, and the false positive rate FPR. So here are the formula for dice, weighted average dice, imbalance, and FPR. So dice score is we know the this is the formula where G means the ground truth and S means the our predicted segmentation. So in the weighted average dice, we have applied an importance to each of the dice for each test cases, and then divided the weighted summation with the weights, with the summation of the weights. So yeah, the weights is actually the intersection between this between the ground truth and the segmented output. So thus we have find and weighted average. So weighted average actually addresses the class impedance by assigning weights to each classes, more reliable than simple average dice in medical segmentations. For tiny regions, it gives a less importance, and for the bigger regions, it gives a more weight to that, so that we can get an overall average. So in the imbalance class, this is the difference between the mathematical average of the dice score over all the test samples and the weighted dice score. So the lesser this value I, it indicates that we have better segmented the tiny regions. So I quantifies the bias caused by class imbalance. It measures difference between class dice and weighted dice. Lower the value of the I indicates better handling of the small tumor regions. And then comes the FPR, or FP is the false positive, TN is the true negative, which measures oversegmentation error, indicates how much non-tumor region is wrongly classified as tumor. Lower FPR implies higher clinical reliability. So this is the comparison result with the base, uh, with respect to the base model. So you can see the imbalance is reduced for the proposed model. As you can see, this is the proposed and this is the base. So the proposed model imbalance measure is 0.1725 and 0.1961 is for the base model, which implies we have reduced the gap between weighted average and the mathematical average. So this is another comparison with respect to the base model for efficiency count. We have reduced 36 billions number, 36 billions of floating point operation counts, and also in the parameter count, we can see the blue colored region is the for the base model, and the white or reddish color region, tiny region is the 1.02 million is the our proposed model, which is uh, much lesser than the base architecture. So this is the comparison with the state-of-the-art methods, which is Glimpse, CDS UNet, and Swan UNet. We can see in whole tumor region, our model performs better than the first two, Glimpse and CDS UNet, but a slightly lesser performance in Swan UNet for the whole tumor regions. But again, in the enhancing tumor region, our model outperforms other two state-of-the-art model for the enhancing tumor region. So this is a tumor core. In tumor core also, our model fails to beat the Swan UNet while beating other two Glimpse and CDS UNet. But in the enhancing tumor region, our model beats all three models. So now comes the efficiency comparison. In efficiency comparison, our model beats both these Glimpse and Swan UNet. So CDS UNet, we didn't in the CDS UNet paper, the parameter count and the floating point operation count were not mentioned. So it was not possible for us to compare this with the CDS UNet, but we compared it with the remaining two Glimpse and Swan UNet. So you can see that in the parameter count, our model performs much better, and it is much lesser than the other two models. And also for the flops count also, it's much lesser than the other two models. So, some of the visual hard test examples we have shown here. So as you can see, predicted masks for predicted mask, ground mask, and the missing region. So we have given three examples: boundary erosion, thin erosion, and cluster erosion. So for the boundary, in the boundary erosion class, we have seen tab. We can see that it almost covers all the ground truth in the predicted mask. Also in thin erosions, we can see that some of the thin regions are missing. But in the cluster erosion, you can see that some of the clusters are quite fully missing. So we can see that our one of the main weakness of the all the existing solutions are to detect these tiny regions, as we have shown in the thin erosion types and the cluster erosion types. These are one of the major weakness of all the existing models. So these are the areas where more work and more effort can be given. So these are the things that I have just said. So these are the limitations. As we have seen that there are multiple clusters of tumor regions. Therefore, a cluster-based algorithm may bring good result. So a cluster-based approach can be explored. As there are many tiny regions, model can be modified from deep inner so that it can learn more from local features. As the proposed method of patch-based approach cannot segment the whole image, it can be generalized so that the whole image can be. So we can take actually a patch-based approach so that we can catch more some of the clusters, and we can go more detail at the granularity level, at more granularity level. So also we can in our solution we have used mean pooling. So pooling can be modified so that it just doesn't focus only on the max value or the mean value. Rather than attention enhanced weighted, a hybrid pooling mechanism can be adopted so that we can get more detailed feature in the encoder decoder architecture. So this can be uh, explored. So in this work, our objectives are partially achieved, as our target was to reduce floating point operations also. So we have reduced it slightly, but we think it's not enough. So it can be reduced more. It needs to be worked. It needs to do work or more work to reduce the floating point operations more, and also some cluster-based or patch-based approach can be explored so that we can better detect the cluster erosions and the thin erosions type cases. So here are the references. Thank you very much.